Can we just?
Yeah.
Okay, good morning. Let me start this off. First of all, as you can see, we are very strict with time. We want to always begin things exactly at the right time. So welcome to Labor. This is me trying to change the slides. First of all, as you can see, we are very strict with welcome to Labor. I'm Gonzalo Chaves. I'm the current president of Species, and I'm just here to kick things off. So I'll try to be brief. So as you know, EvoStar is comprised of 4 events: EvoGP, Evo Operations, EvoCop, and Evo Mozart. EvoGP is occurring since the very beginning of EvoStar. In fact, before EvoStar started, and Evo Operations also running from the beginning. EvoCop started 3 years later, and Evo Mozart started 13 years ago, actually as a conference before it was a workshop, I believe. So this year we also ran a special joint track on evolutionary machine learning. This is a joint track between EvoGP and EvoApps. And of course, we also have the late-breaking abstracts that are organized by Antonio. So what's next? Let me do some quick introduction to the logistics of this event, and I hope to get these things right. So, the helpers. These are those guys in golden yellow shirts. So if you have problems, you talk to them. The keynotes will be here in this room. This is room A, but it also has other names, so this room, on PS6. Complicated. So B, C, and D are in the registration building where you have already been. This is your badge. Please keep your badge. If you find Ernesto Costa badge, return it to him. He already was able to lose it. So that's it. The lunch and coffee breaks will also be in the same building as the registration, but there is a large room where we can have the coffee breaks. The poster session is also there, in the coffee breaks room, and the banquet will be at the Art Center. It is a different building very close by. Wi-Fi, I believe all of you are already able to log in. You have everyone, you also have the guest network. I believe everybody has everyone, at least most of you have it. So that's it. I believe all of you. So today we have 4 sessions. Then in the other days we have people sessions. The Zoom meetings are free. If you are sharing an event, please, that's it. Go to the golden yellow guys session, guys with the yellow church. You understand it, and make sure that you are broadcasting through Zoom, and make sure that people on Zoom can hear you. And when there are questions, please remind you that there are people on Zoom, so you need to pass on the mic or repeat the questions for those that are attending on online, otherwise it won't be good. So the closing session will also be here in this room. We do the best paper award announcements and many other awards announcements. And Friday in the afternoon at 20, we have the AGM of the Species Society. You are welcome to join. If you have registered for EvoStar, you are automatically a member of the Species Society, and we will be discussing important things. There is also at 3:20, I thought I had this slide here, but maybe I don't. There is an option of Friday excursion, if weather allows it. We are counting on a very sunny weather. This is typical in this area. So this will be a walk around the town, I believe, trying to make things. It's a lovely location, so if you want, please take note of that. So the keynote speakers, let's talk into that. So right after I shut up, we will have John Dinis, who is over there. He's going to talk about evolution, immunity, and robots. And on Friday, we have Sabine Wirth also doing the closing keynote. Everything is live streamed. Species YouTube channel, but probably won't be recorded forever. Okay. And Friday, we also have the Julian Francis Miller Award. This is the second year that we are giving the award. The award celebrates Julian's achievements and contributions to science. And we have all this information on the webpage, so if you want to nominate somebody for the award, you can do it until the 31st of July. Then in November the 1st, the jury of the award meets, creates a short list, sends it to the executive board of Species, and finally there is a decision of the executive board. In practice, the jury decides and we validate that decision. And then the award in this event. And this year you have two winners of the award. The first is Dario Floriano, that will join us later today for their contributions for evolutionary robotics, and also have Lutzen also for the contributions to evolutionary robotics. Unfortunately, our president made it that he will be attending online and he is going to participate in this event during the Julian Francis Miller Award session. We call it Coffee with Us and Dario. This will be shared by Mark for an hour. It's just an informal talk between people. And please, if you have questions, and this is an opportunity to make questions to people that are really interesting and made important contributions, please send your questions to this address. Oh, regarding the logistics, I forgot one thing that Christine asked me specifically to say. If you need a certificate of participation, you need to go to registration, ask them a certificate, and they will give it to you. Okay? This is maybe not right now because they are a little bit overwhelmed with people arriving. You have time, but don't forget you need to ask for that. Okay, and please send these emails asking interesting questions. That's a cool way to participate. So, also, we like to give awards, and we have best paper awards for EUGP, EvoCop, EvoLabs. All of these give best paper awards. At the end of the session where the paper is presented, you have an opportunity to vote. And your vote counts, of course, and that's how the awards are decided. We also have the Outstanding Students Award, the Best Student Paper Award, the Best Paper Award, and the EvoStar Dissemination Award. So plenty of opportunities to get an award and get an amazing T-shirt and other wonderful prizes. It's just a T-shirt, isn't it? Okay, I assume so. So, students, here is the students crowd. Yesterday we had a meeting in the afternoon. If you missed that, well, it was great. It was a fantastic event. There is a student workshop on Thursday at 12:20, and there is a scavenger hunt. I really don't know how this works, but again, you have more prizes to win. Fantastic event. And then, as I told you before, you have the species AGM, and Species is a non-profit society, of course, and it really depends on the goodwill of every one of us to contribute and you can also contribute with money if you want. We are looking for society. So please participate on the AGM. We need to elect a new executive board and so on. You can apply for the executive board and all of these matters. Now, João and the rest of the crew that is doing the publicity of the event, they are working a lot. We have just recently created the LinkedIn account and we are switching to the LinkedIn because, as you know, Facebook is basically dead. There's only old people and this is also important for the event. And if you tweet, and I know that a lot of you tweet, please, as you mentioned, EvoStar conference and use the hashtags. Okay? Other opportunities, and as you know, or maybe not, Species is a society for the promotion of evolutionary plantation in Europe and surroundings. That's the S, final S in Species. We are trying to expand our activities, so we offer scholarships. These are 3-month stays, and we contribute with 900 euros. That institutions can apply until the 15th of May, and then the students and the postgrads, so recent PhD holders can apply until the 30th of June. Christine, as our host, has also been taking care of the scholarships until this year. This year, Inaki, we have taken over, but you have all the information on the website. And I can see lots of people here which have received a scholarship and published papers resulting from that scholarship. So please take advantage of these. You can and you should apply. So ongoing, well, this year Francesca already finished her scholarship, and then we have 2 other students that are starting their scholarships right now, Gloria, Eddie, and Pepper. We give these scholarships per year. Another opportunity, right? Another opportunity is to participate on the summer school of EvoStar and of Species. And these will be hosted in a terrible location, as you can see. It's Merida, Spain. It's very convenient. It's the 3rd year we are going to organize it in this spot. As you can see, it's a nice spot, and the food is good. The weather is nice. I only participated last year, and I have to give credit to Anna. I wanted to change the location, but now I'm entirely convinced that we should do it there again. So again, this is I call it. I only participated. Yes, sorry. So this is also an opportunity for you. And final, first of all, I want to thank Christine Zarts, which is over there. Where is Christine? Come on. And the staff, the yellow shirt guys. Thanks for organizing this. It's been lovely so far, but I'm sure it will be a huge success. Then the EvoStar, the graphic identity team, João, Sergio, and Jessica, which are around there somewhere. There's lots of work going on behind the scenes, and this is a huge amount of work. In fact, 2 of these guys should be finishing their PhDs instead of doing graphics for EvoStar. Around there somewhere. I'll talk with their supervisor about that. So thanks, that's been great. Let's clap for you. And also the task force, the electronic task force with Anna, the EvoStar coordinator. Anna disappeared right now. Anna is there. Corona, Zakaria, and many others. And also the even saw student affairs officers. So that's Georgia and Jessica. Stand up, stand up. And last but obviously not the least, I'll invite the speakers, John Timis and Sabine. I don't know if she's here or not. So anyway, let's clap for them. And that's it from him. So Christine, please don't come to the stage and join if you want. Anyway, let's clap for them.
Oh, sorry. Hello, everyone. So, right. I normally run around in the lecture theatre, but anyway. All right. So everybody will see me. So maybe as a local organizer, you shouldn't be introducing the first keynote speaker because you tend to be very busy. But I couldn't resist introducing John today because I'm really thrilled that he is our first keynote speaker. So John is a truly interdisciplinary researcher. So he's working in in robotics and computational modeling. And my understanding is that if we get the computer to work, he will take us on that adventure. We need the meeting thing. Okay. Right. So let me say while they're setting up a few words about John's career. So actually, John is a graduate of Aberystwyth University. So he's done his undergraduate and his PhD in the Department of Computer Science, and then afterwards moved to the University of Kent as a lecturer, became a senior lecturer there, then moved on to the University of York as a reader, then professor, then head of department, then provost chancellor for partnership and knowledge transfer, not all at the same time, I should probably say, but in that order, and then moved to the University of Sunderland in the north of England as a deputy vice chancellor. But as you hopefully agree, Aberystwyth is too nice to stay away for too long. So he came back in January this year, and what would be more fitting than actually becoming the vice chancellor of the university. Right, so on a more personal note, so actually I know John for quite a while now. So my whole PhD was based on one sentence in one of his overview papers on artificial immune systems. Shortly after I met him at a summer school in Italy, which kind of drove the direction of my PhD. So I really couldn't resist introducing him today, and I couldn't be more thrilled to have you as the first keynote at a conference that I'm organizing at our university. So if we are ready, well, or in any case, please give a very, very warm welcome to John Timis for the first keynote.
Morning, everyone. Just give us 1 second. It's nearly there.
I don't know how to switch these in.
It's okay. Well, thank you. Okay. Morning, everyone, and thanks, Christine, for that introduction. It's a real privilege to be here with you all this morning. As Christine said, it's kind of strange, actually, being back here. So, as Christine said, I'm now the Vice Chancellor of this university. Those of you who don't know what that means, it's like the President of the university, I guess, if you're from kind of mainland Europe. And I came back here in January. And so, but I got asked to do this talk way before I even thought about applying for the job back here in Aber. And so what I'm going to do is take you on a little bit of a journey, I guess, of work for the last, which is scarily 30 years, actually. And I was chatting with Emma earlier, and
I kind of feel old now, and so I wear a suit and I've got grey hair, and it's kind of strange actually being at an event like this now. I remember coming to events 30 odd years ago, sitting there listening to people like me, and all of a sudden I'm here, and it's just gone really, really quickly. What I'm going to talk to you about is work that I've kind of, a journey really, rather than a technical talk, a bit of a journey that I've been on, working particularly with immunologists and other biologists over the years, and looking at how to both do bio-inspired systems, with my focus pretty much has always been on the immune system. Actually, I'll talk about that a little bit in a bit. But not just using it in terms of being inspired for different algorithms and designs and so on, but actually how I, as a computer scientist, trained as a computer scientist anyway, could actually then have input and help develop the field of immunology and an understanding of things like therapeutic design and how those things interplayed, and then how it kind of morphed into playing with robots, and then how it then morphed again, working with a load of software engineers. And even though I'm trained as a computer scientist, I've now learned over the years software engineering is a completely different discipline. Yeah, and I'll talk a little bit about that as well towards the end. So hopefully these slides are all going to work. Yeah. So when I started off, biological systems are really interesting to me. I started, as Christine said, did my PhD here, and I worked on the immune system, and I looked at mechanisms for learning within the immune system, particularly networks, and how immune networks, there was a theory around at the time around how these networks learned and adapted over time, and I was really interested in that. And so that's kind of what I worked on. And that led to all sorts of ideas around self-organization and looking at how the immune system is a self-organizing system. So I was very interested in that. And then, of course, I started learning then about evolutionary computing, and I was also interested in that. The problem is everything's really shiny and everything's really interesting. And so early on, I was interested in all of these things and looking at underlying properties of how systems self-organize, what you can do with them. And then importantly, I was interested in how you get them onto hardware, really, and how you get them into robotic systems. And on the immune system, I was really interested in how it managed to learn about new information and how it retained that information over time and the mechanisms by which that came about. And then more subsequently, looking at how you can evolve all of these things as well, and looking at combining all these different areas together, which turns out to be really difficult. So I worked on all sorts of interesting problems over the years. So top right video is from a colleague, Alan Winfield, but I spent a long time looking at kind of swarm robot systems, and I'll come back to that from an immune system perspective in a bit. But looking at not only just modeling of them, but then how do you actually build them and how do you actually get them working together? And I was really interested in what happened when they broke, basically. And so, because of my background within the immune system, is a lot of it is about detecting when something goes wrong and then looking at trying to initiate some kind of recovery. That kind of led me to thinking around kind of recovery mechanisms. We flirted with underwater robots for a while on a European project, which was absolutely bonkers. I think that's probably the phrase I would use, but great fun. Nonetheless, it was really great fun. And looking then how we could kind of do self-repairing systems underwater. And particularly what we looked at there was looking at being able to do a relay chain. So if you had robots that were forming, looking around on the surface, on the bottom of the planet, of the ocean or water, how would you be able to get information back up in a reliable way should some of those units fail? And looking at self-reconfiguration. And so we did all that kind of based on immune system principles underwater. God, this is a nightmare. Right, okay. So, been talking about the immune system, and that's kind of what's kind of interested me over the last kind of 30 years, really, looking at how the immune system works, how it doesn't work, and lots of different theories that underpin the different mechanisms there. So at a very simple level, the immune system is something that protects the body, the host. There are a number of different kind of areas, aspects of immunity, some that you're inherently born with, called your innate immune system, and then ones that you learn over the lifetime. That's kind of where your adaptive immune system comes in. And both of these mechanisms, both of these systems are really interesting computationally and have some really interesting properties about what they can do, the kind of patterns they can recognize, and how they remember those and how they adapt to them over time. And so particular of interest is the adaptive immune system, where I focus most of effort, a lot of people working in this area did as well. And this is looking at when you get an infection of some kind, then what is the response the immune system kind of gives? And so it recognizes where it can, the pathogenic material, the thing that causes the response, and then there's a kind of cascade response comes on then with different cells kicking in over time in order to try and eliminate and remove that infection from you, over time. And that mechanism is a kind of pseudo-evolutionary type process, and it's a learning process as well. So when the immune system responds to a particular type of infection, it will learn to identify that one, but will also generalize a little bit as well. And so it will then, that's why, if you get infected with one type of kind of pathogen, something that's quite similar, the immune system will recognize it again. And certain vaccines work on that principle of being able to recognize a kind of broad spectrum of different types of things. It's because the immune system is generalized from specific examples. And then there are mechanisms of how the immune system remembers. There's the whole aspect of immune memory, so how cells hang around effectively. So when you get infected 2 or 3 years later, your immune system can respond really quickly. And again, that's the basis of a lot of vaccines. And so some vaccines will last a year, some will last 6 months, some will last 5 years, some will last your lifetime. It just depends. But it's all through priming the immune system and the immune system being able to remember these different kind of infections over time. But it is a really interesting, fascinating system that is complex and it is adaptive. And you see lots of kind of really interesting self-organizing behavior in the immune system, as well as evolution, as well as learning, as well as adaptation too. That's why it was interesting. And so for me, I always ended up working with immunologists early on. And are there any immunologists in the room? Good. Because they're a bit weird, right? Because so you got to be quick careful what you say, but they use lots of long words, right? Lots of them, and they use lots of acronyms, right? It's a complete and utter nightmare, but it takes time. And so we're doing interdisciplinary research for me. A jack of all trades is a kind of colloquial phrase of someone that's kind of good at a bit of everything, but not specialized in any one particular thing. And so what I've found over the years is I know a lot about little bits of everything, but not a lot about one very specific thing. But sometimes that's not such a problem. One of the things I had to watch for over the years, and I know other people have this issue as well, if people find out you're a computer scientist or a mathematician, they'll come and ask you about the computer science problems or the maths problems, and then try and solve that. And actually, that's kind of not necessarily the most interesting thing. Actually, the interesting thing is what's at the intersection of the disciplines, the intersection of the areas, where your skills can help shed insight into what the problem they've got. So a lot of the immunologists I worked with over the years, they were very reductionist experimentally. And I came from a systems background, and we were looking then at a more systemic level and asking system level questions of immune systems. And that kind of fundamentally changed how they did their experimentation, because you come from a different, you take a different perspective. It's great that you work from people from different backgrounds. You get to apply what you know in a different area, and you get to be the really stupid person in the room, which I quite like, actually. You ask the dumb question. You say, why is that like that? Tell me. And often people would say, actually, no one's ever asked that before. Just is. And those kind of challenges that you bring because you're a little bit naive, or you have a slightly different perspective. You have in my case, a computational perspective, you are giving a slightly different lens on the problem. And so you learn about new areas, you learn about your own areas. But it wasn't easy, and it never is for everyone. I know there are people in this room who have been on a similar journey who will have different experiences to me as well. And had some and some good things and some lots of good things. It takes a long time to get right. And the key thing I found was actually developing the common language so we could understand each other. That actually was really difficult. And just trying to get a feel for what do you really mean when you say cell or system? What's a system to you? What's adaptation to you? What's mutation to you? And asking those kind of really basic questions was quite useful. And it turns out having the right people around you and the right team is really important. I've been very fortunate over my academic life, and I've worked with some simply outstanding people and outstanding PhD students in particular, who have just been incredible. And they've pushed me as much as I've pushed them, actually, in terms of those journeys. And they've been able to kind of really get into some of the detail that I wasn't able to do. There are issues around funding, always have been. I'm on a funding panel at the moment, and I can't believe I'm having the same conversations we had 30 years ago. I can't believe it, you know, around, oh, well, that's not really the kind of thing we fund, is it? Because it's doing wet lab experimentation. We were discussing that 30 years ago, and I thought we'd solved that problem, but it's still in places, it just drives me nuts. Yeah, it's just incredible. And publications similarly. And interestingly, the end of the talk, I'll talk a little bit about some of the software engineering work we're doing in robotics, and you'll see how it links into everything, hopefully. One of the problems we're having there is the roboticists don't like the software engineering, and the software engineers don't like the robotics stuff. So actually trying to publish this stuff is really difficult. It's really difficult. And it's just like, just my head in, yeah. So anyway, so I'm just going to give you a very quick early experience of where I learned some of this. With who's now a friend of mine, Vipin Kumar, who works over at UCSD in San Diego. So I met Vipin at a little workshop conference. We got talking, and we ended up developing like well, I've known Vipin now for like 15 years or so, I guess. But we had PhD students together, we've had grants together, we've had different bits and pieces. But the early days with Vipin were really interesting for me in terms of doing it. And so I went to his office. He saw a talk that I gave around artificial immune systems and modeling and so on. And he said, oh, I've got a really interesting, simple system I want you to model, because I think it could be interesting from a learning. Brilliant. Okay, good. So the first conversation went roughly like this, and I can still remember it sat in his office, San Diego. He said to me, we've got 4 cells and a few interactions in this system of mine that he works on. Okay, his system he worked on was called experimental autoimmune encephalomyelitis, yeah, which is like it's a mouse proxy disease for multiple sclerosis, right? So that's the kind of context working in. So it's 4 cells and a few interactions, and I went, that should be quite easy, right? That's what I said. And then he showed it to me, and I said, this is a bit harder than I first thought, Vipin, because actually it's a bit more than 4 cells, isn't it? And it's a bit more than a few interactions, isn't it? You know, yeah, I kind of thought it was really. Yeah. And so after 3 years, it was lots of visits. I had to go to San Diego a lot, which is just awful. Really bad. Yeah. It's one of my favorite places on the planet. Conference calls and ibuprofen, and we got through a PhD student or 2 as well, bless them. Yeah, on this. We did develop a model and simulation that we thought was okay. But that initial realization of the complexity of the system, just by asking some basic questions, was quite profound, both from his perspective and also from mine. Yeah. So what we ended up with was something, I'm not going to go through the detail, but it basically looked like this. Yeah. So those of you can count, which is all of you, hopefully, there's more than 4 cells there. Yeah. And there's more than a few interactions as well. And it turns out some are positive interactions, some are negative interactions, different feedback loops, and all sorts of things. But this is a model that basically is a regulatory network, that regulates the immune system response in an autoimmune context when the autoimmunity is induced in the particular mouse. Yeah. So you've got lots of different types of cells, and it's all complicated. It's all in different compartments of the body, it turns out. Some of it's in the blood-brain barrier as well, and it's a nightmare. So actually, we ended up with this kind of agent-based model of 5 compartments, all with different types of cells. It was fully connected, that allowed things to flow through. So a full physiological model. And it allowed us to do all sorts of really cool stuff, including a splenectomy, which is basically the removal of the spleen. So we modeled the spleen, and we could then actually reproduce splenectomy experiments by disconnecting the spleen from the system. Yeah. And so we did all sorts of cool stuff, looking at how to model the results that we got from our in silico experiments. This is the severity index of the disease. So basically, as you induce autoimmunity into the mouse, this disease, it kicks in and there's different states of paralysis. It's pretty grim, if I'm honest. Yeah, but that's how it works. And so we had to kind of create a severity index for the simulation as well, and calibrate our systems against the kind of in vivo experimentation, which we did. And we did all sorts of things. Talked about the splenectomy, which was kind of interesting. So we could reproduce, and we managed to reproduce results that were published elsewhere, not from our own work, but we reproduced other work from it. And we also did things like looking at the effect of these things called T cells, which are a really important immune system cell on autoimmunity, looking at how specific the T cell could get in order to recognize something and mimic that intervention through a drug intervention effectively, and looking at how it would bind to neural cells. And what we found is actually, unless the T cell was very, very good at binding, actually you made stuff worse. Yeah, you made the condition worse, in fact. And this backed up results that were published independently from ours as well. So we kind of tested our system against those results and we managed to reproduce other people's work through this model, even though this model wasn't designed to do that. So we could kind of we could play around with these models just to experiment. And this was really useful for Vipin, because what that allowed him to do, and subsequent people I've worked with over the years, is to guide their experimentation through the use of mathematics and computational models, and more recently AI models as well, rather than replace. It doesn't replace completely, yeah. But what we've managed to do is kind of helpfully reduce and help guide those experiments so they know which experiments to do. So we learned a whole load of doing this work, and we did lots of other stuff too, which I won't go into as well. But one of the things that kind of jumped out, this is where the journey on the software engineering piece started to come was a lot of the models, even they were a bit black boxy, right? Even though, yes, you could get into an agent-based model, yeah, you could look at it. It's quite complicated. There was a lot of assumptions, yeah. Often they were hard to interpret for people. Often they were based on little data. People, particularly we were working with a lot of pharmaceutical companies at the time, they wanted to be able to explain stuff and understand what the model was doing and why. And they wanted to have confidence that the simulation you produced was actually, the results were a result of the simulation, not as an accidental artifact of the model because you got the coding wrong or you've made some kind of weird assumption. Yeah. And that's actually quite hard to prove to someone. So you're saying, well, if I'm going to inject someone, if I'm going to design a drug and spend £500,000 doing this experiment, I want to know I've got some confidence in this model. It's not unreasonable for them to do that. And at the time, we couldn't really give that, to be honest. And so we kind of set about looking at an engineering process, looking at how you go about building these models in a principled way, so you could embed in your assumptions, the detail, the annotations, and all that kind of stuff. So you could then give particularly pharmaceutical companies a bit more reassurance that your model was actually meaningful in that regard. Yeah, and the results you got out were meaningful to them in a particular context. So we developed, this was a big project on one slide with a lot of people involved, where we kind of developed a whole process for developing these simulations, both mathematical ones and computational based ones as well, where we could trace very well the assumptions, how we embedded that into the mathematics or into the models, how that then reflected in the results that came out, and how we reflected that then back to the domain of the domain we were modeling in particular. So it became a lot more transparent for people. Now, we did add extra work in, but it made the whole thing really transparent, okay, which was good. That allowed us then to work with people like AstraZeneca. And so there's just a couple of slides on this. So some of the work that came out of that modeling, we did a lot of work on fish and looking at modeling fish. And again, using the similar models and looking at the immune response, well, kind of toxicity response actually for fish. And we developed this virtual fish lab for AZ, which now they own. So we spent quite a few years with them, and this basically allows them to do, if you're testing active pharmaceutical ingredients, you have to physically do it on fish, right? There's no European regulations, British regulations, American regulations. You've got to do it on fish. right, in order to do it. But they kill a lot of fish and it costs a lot of money and it takes a lot of time. So we basically automated that whole process for them. And so that allows them to run a 3 or 4 month life cycle study in about 20 minutes and save them about £500,000 each experiment. So it didn't replace everything, but it allowed them to then go and say, this is the experiment we're going to do. Yeah. So it allowed them to do that, which was good. And they had the confidence in the system because of the transparent nature of the way the model was developed. So that's on the modeling side. Kind of bring it through. Is this coming through into Zoom? Is it okay or not? Well, no one said anything, so okay, so I'll keep going. So the immune system and then going into kind of the robots, which I mentioned earlier. So from a fault tolerance perspective, when something goes wrong in a system, you need to detect the error. Yeah. You need to be able to diagnose it. What is it? Yeah, what is it that's gone wrong? And then initiate some kind of recovery mechanism. That's the kind of fundamental basics of kind of fault tolerance and stuff. And over the years, we've looked at how the immune system does each bit of this. Yeah. Now the immune system does detect. Yeah. And we've talked about cells and how they may detect and recognize certain types of pathogenic material. The immune system doesn't really diagnose in the classic sense. Yeah, not really. It doesn't go, oh, you've got X. Yeah, it doesn't do that. Yeah, but from an engineering perspective, you need to kind of be able to say what's actually wrong. And the immune system certainly does recover. It certainly does initiate recovery mechanisms, either through the elimination of the infection or the repair of tissue. The immune system will create structures as well to try and kind of protect the body from further infection. So it builds things with different cells. It does all sorts of different activities that are part of its recovery kind of cycle. And clearly it doesn't always work, but it works pretty well. And so what we did is looking at individual robots. There was lots of work looking at detecting faults internally to the system. Looking at, okay, what's gone wrong inside that, whether it be a faulty sensor to misreadings or whatever it is, but also detecting anomalies externally. So what's affecting an individual robot that's external to it, but is causing it somehow to go wrong. Yeah, so that could be kind of interference, signals interference. It could be a dodgy ground. It could be someone's bumped into it or whatever. So looking for anomalies externally. And then looking at, we did a lot of work on individual ones, but then looking across at the swarm systems, looking at, and this is work we did a lot with Alan, was looking at, Alan Winfield that is, looking at detecting a fault within an individual, first of all. So you've got 15 or 20 robots running around. Individual robots could fail, or individual bits of a robot could fail. So that's one thing. So you can do that, yeah. Or, and the individual can be responsible for detecting that. Or more interestingly, actually, is identifying the fault within an individual by observing from someone else. So someone else tells you you're wrong. Yeah. So I can look at you, I can see what you're doing, and say, actually, you're not behaving how I expect you to behave. Yeah, it's an anomaly. And the immune system works on principles of anomalies. And so that's the kind of what we harnessed, identifying that. And so we managed to build systems that could do that. That you could introduce faults into a robot system, and then the swarm would then could collectively decide by observation on it what's going wrong. Yeah. And so we could also then look at, like I say, detecting those individual faults, diagnosing them as well, saying, okay, it's this particular sensor that's gone, or it's this particular actuator, or it's a consequence of A, B, and C that's gone wrong, and then mapping that to recovery mechanisms, which would either be things like shutting the robot down, because sometimes in swarms, 1 or 2 of them fail, it's kind of fine. But actually, worked for a long time ago now, kind of showed that there were issues with scaling with certain amounts of faults in swarms, and so you couldn't rely on that completely. And so it may be that it would instigate some kind of repair. If there was faults with the power, for example, we could initiate kind of self-recharges and that kind of thing, or even self-reconfiguration if necessary. So those kind of things were possible in terms of those. But that's all based on some of the models that we then created back the EAE model I showed you, that regulatory model, that proved to be quite useful actually in terms of understanding how different cells interact and respond and then initiate different recovery type mechanisms. So more recently, and there are people in this room who are much better qualified to talk about this than I will, so I've only got 2 slides, so I'm not going to embarrass myself about it. But I got involved in a really interesting project that initially I called What If Robots Could Design and Build Themselves? But it wasn't called that at all, actually, but that's kind of what I thought was really interesting. And it started with Gus Iben, who many of you will know, and Emma, who's now in the room as well, whereas Emma's around there somewhere. This is a paper we wrote that came out of a kind of an interesting, I won't say doomed, but it was an interesting project called Symbrian a long time ago. Yeah, it was a European project. And these are the collaborators we worked with at the time, and looking at evolving robots. We were interested in that project and looking at using evolution to evolve the design and the reconfiguration of the systems, and we got kind of frustrated with it. You know, we basically didn't work. Yeah. And so we thought about what would it mean to evolve robots in real time in real space. Yeah. And there's an interesting paper that Gus led quite some time ago on this one. And this was the kind of the genesis of an idea that he and others then ran with, and I was involved with a bit over the time. And so, yeah. So this was a project that we tried to get funded 3 times through the European Union, I think, at least 3. Wasn't it, Emma? Yeah, 3. EU kept saying no. We thought, right, get rid of that. So we went to the UK funding body, got rid of a load of people, yeah, unfortunately, because obviously they couldn't get the funding, stripped the project right down, and put it to the UK funding council called the EPSRC, Engineering Physical Sciences Research Council. And this was a absolutely bonkers project, right? And they said yes. I think, was it second time or first time? It was first time, wasn't it? It was first time. And they said yes. And they gave us a lot of money, basically, to look at building, and I'll show you the video in a second. How do you go about building, designing a system that allows robots to evaluate a design, both the hardware and also the controller, yeah, fabricate it, yeah, test it, and then integrate what you've learned back into the evolutionary process again and do it all again, over and over and over again, right? That was the basic idea. So you could then, in theory, you could create a factory, if you like. Yeah, you could just send off somewhere and we'll just go and build stuff for you. Right? It was absolutely crazy, but they said yes. And so the kind of basics that you needed to do that, and this is a very crude kind of explanation of what is now a very complicated kind of system, yeah, is that you need to be able to have some evolutionary algorithms to be able to work in the virtual environment. So we used heavily simulation in order to evaluate both the hardware design of the robot, but also the controllers that go in there. And then you also needed to fabricate them and test that and use it in a physical environment as well. Yeah. And so use a number of evolutionary algorithms and learning algorithms as well, once they're made, observing the robots in the environment and trying to feed back into that whole evolutionary process. So you've got that kind of closed loop hardware evolution. Yeah. So this was a kind of a picture that I can't remember who drew this now, actually, if I'm honest. Basically kind of just outlining the concept of it, which was you had a fabricator, yeah, a robot fabricator that would kind of create the robots and build them for you. You had the training facility where you would put robots in a little environment so it could learn and explore, and you could do some learning, adaptation, and then eventually you think they were good enough, they could go out into the world and do stuff. Yeah. And then it was all kind of closed loops. You can then observe that, learn what you learn, and feed back in to the evolutionary process. And also, you could look at evolving both virtual and physical robots at the same time in the simulator. Right? That was the idea. And so, lots of learning. I thought I'd taken this slide out. Anyway, never mind. It's here now. What you've got is, one of the big challenges you have is if you can evolve whatever you want, but actually, can you fabricate it? Yeah. And so you might have a whole area of the search space that's really interesting, but you can never physically be fabricated. And so you need to be able to kind of make sure you can do what we call a viability test. Yeah. So you say, actually, yes, you can evolve this one. You could do something, and in virtual system, it's fine, but in reality, it's never going to work. Yeah. And so we had to kind of introduce that kind of viability into the red square in the middle, which is really, really important. So you could make use of the evolutionary space, but then also produce physical robots that were meaningful and could do something with. So this is just a quick video of the simulator on the top, and then the physical representation on the bottom of it. And so what we ended up doing over time was, clearly we couldn't build everything from scratch. And so we had to have certain kind of pre-made, pre-designed kind of component pieces, and then look at evolving the structure of how you connect them together, where the arms would go, where the actuators would go, where the sensors might go, that kind of thing, rather than doing the whole thing from scratch, obviously. And so we could do a lot in the simulator. So you could evolve that in the simulation, and then at a certain point, you then fabricate it. Okay, and then that's the robot you would get down at the bottom, and then you would allow it to learn online there. And this was the fabricator system that was built. Yeah, obviously this is sped up. It's a bit slower than this, but you've got kind of a base unit component for the robot. You've got different wheels, different sensors that are being put on. And then those wires, they caused the postdoc Matt a lot of headache over the years. Turns out wires were really difficult. Yeah, we came up with a very cunning solution on how to do that with flexible bendy wires, effectively. And then the robot that's building it is pre-programmed in order to do that, but it's left alone to fabricate the robot on its own. So it's got a design. It's got a populated kind of bed of different component pieces. The evolutionary processes run through. It says, this is the robot to build. It builds it. Yeah. And then takes it off the fabricator and sticks it into the arena, which is what you saw down the bottom. And the robot would then go off and play. And we'll do a whole load of more other stuff as well. You know, if you want to know more about that one, I'd recommend the TED Talk by Emma, which is worth a watch. Yeah, Emma Hart. It's worth looking at that. And that she goes into a lot of detail about that particular project. But it is really very cool in terms of what they manage to be able to do. Just for the last kind of 5-6 minutes or so, so we'll talk a little bit about kind of software engineering for robotics now. So I talked about software engineering in the context of building the models and the simulations and importance of that. And that was about process. About 6-7 years ago, I started talking to proper software engineers, as I might call them. Yeah. I don't know how many of you are computer science graduates, but when I was a computer science student here, a long time ago, the most boring lectures I ever had, and I'm sorry if this offends anyone, was formal methods. Right? Seriously, I couldn't wait to leave. Right? I could never quite see the point. You know? And then it all became clear to me about 8 or 9 years ago why they're so useful, actually. Yeah. And so I started working with a formal methodist, actually, which was like working from some completely different discipline, if I'm honest, completely different. Yeah. And what they were interested in, being blunt, was working on interesting problems because they worked on relatively kind of modest, small problems. And I was really interested in kind of controllers for robots and getting and issues we found and you will find when you simulate and then you've got the gap between reality and the hardware and you're having to mess around with it, that kind of stuff. So I was interested in that as well. And it turns out that actually these things came together quite nicely. And we managed to get a collaboration going, get some money in order to start developing some ideas about being able to do what's called model-driven engineering. So what you do is you develop a model of the system, you develop the model of the hardware, you develop a model of the controller and so on, and everything's then automatically generated. And then the testing and the formal method analysis of the system is automatic. And that allows you to have some confidence around what you've got written is actually on the hardware itself, but also helps you kind of figure out those gaps between the simulation and the hardware as well, actually, which is really important. Yeah. And I still have one PhD student left, and he's working on the physics engine bit of this, really, which is then looking at how you kind of make a bit more transparent the equations that underpin the physics engines in robotic simulators. And then if you are generating code automatically and you want a certain behavior, you can then trace everything from the code all the way through, including the physics engine, to say, actually, no, we know this is working in this particular way. So typical approach to building, or certainly I used anyway, is you typically have to building a controller for a robot. So we might evolve it, you know, you might use a neural network or whatever it is. But actually what you tend to do is have an abstract, relatively abstract model. I use a lot of state machines in the time, and a lot of the stuff I've done in the past has just been basically state machine based. You use some kind of simulator, you kind of hack it, you draw a little diagram, you go, yeah, that's about right. You code it all up and you get it working. Yeah, simulation. You get it working on your robot in the simulator, and then you go, right, okay, I'm going to transfer that over to the hardware. And usually it kind of works, but doesn't quite work. And you end up faffing around a bit, and eventually it works. And sometimes you don't even bother with simulation because it's too much hassle. So you just go straight to the hardware. Yeah. And none of that's ideal, particularly if you want to work in systems that are of critical importance or safety critical systems in particular. Yeah. Or where you want some kind of guarantee about performance. The drone will not fly above 1 meter. Yeah. And you can guarantee it. And I mean mathematically guarantee it. Yeah. Well, most of the time it doesn't fly above 1 meter, but every now and then it might. It's not really going to cut it. Yeah. So those are the kind of things those kind of areas I'm talking about. We have something called RoboStar, not EvoStar, but RoboStar, yeah, approach, which is we effectively model the hardware, and we model it through effectively a variant of UML, yeah, Unified Modeling Language, which has a very strong semantic kind of underpinning that we've created for our variant here. So we actually model the hardware itself, so you know what you've got. We also then model the controller itself, and the controller is modeled through a state machine, and again, very rigorously modeled, with a very clear kind of semantic underneath, and crucially a meta model for all of this as well. And that'll become useful in just a second. Yeah. And then we also model the world, the environment as well. So we do these three things. So then, and by modeling the world in this context, what I mean by model is this is a mathematical representation of the hardware, a mathematical representation of the controller, and a mathematical representation of the world, okay, of it. And we use domain-specific languages in order to be able to do all of that, yeah, which then map into from a graphical front end. So everything you do, you just draw diagrams, basically. Yeah, effectively, that's what you do in the system. And then with a model-driven approach, the nice thing is what you do is you develop the models, and then everything's automated afterwards, right? The whole code generation is automated. The testing is automated. Everything's automated on it. And then the analysis you do, i.e., will the controller of the drone not go above 1 meter? That's all automated. And then we can test that within the framework, yeah, of it. And then if you find problems with it, if you report, you test, if you find problems with it, you don't fiddle with the code, you fiddle with the model, because it's the model that's wrong. Yeah, that's the whole premise of a model-driven approach. Yeah, and so you kind of close that loop on it. And we've managed to create this, it's all done in Eclipse actually, so maybe there, but you can develop the model, generate your simulation code. It's a curated model. So the work I talked about earlier with AstraZeneca and the FISH project are looking at well-curated models. We use the same technology in this, right? It's exactly the same underpinning technology. So we could then have a curated kind of model that we could write reports on effectively, yeah, about it. And then everything is automated in that approach, yeah. And when we do testing of systems, and again, this has always been difficult in any of the work that I've done in the swarm work, individual robot, the evolutionary stuff, testing it is always a bit of a nightmare, right? And so actually, the model-based approach lends itself well to a kind of an automated approach to testing too, yeah? And so what you can then do is set up a load of tests for the system, introduce faults and failures into the system, and then automatically identify them, yeah? And The interesting bit around the test generation is what we call mutation testing. And so what you're doing there is generating a load of effectively changes in the model. A mutation in this context might be moving a less than to a greater than sign, right? It's a trivial example, but that's kind of an example. There are lots of other ones. But you mutate the model, right? And you can use evolutionary approaches for this. You could use exhaustive approaches for it. You can use all sorts of things for this kind of approach. Yeah. But what you do then is just saying you're effectively alter either the behavior of the controller, you test that, or you can alter the world, or you can alter the hardware, and you can test all of these things. Yeah. Through it. And the interesting thing for me now, if I had more time, which I don't, not now, but that sounds awful, doesn't it? More time. I'm not about to die or anything like that. If I had more academic time in order to do that, this is kind of where I would probably end up start focusing, actually, because I think there's a whole interesting piece of work around how do you take the basics of automated testing and wrap it all up in an evolutionary loop, right? So if you then start to automatically test everything that you're evolving, all within this kind of framework. So you've got a whole load of tests, exhaustive tests that you could do. And as I said, you've got automated code generation as well, with different tests that run in different scenarios. And there's no programming costs associated with it, which is really interesting. So I've got two bits of a puzzle here, which I haven't quite put together in my head, right? You've got the puzzle of the evolutionary approach and evolving the hardware, the controller, and all that kind of stuff, right? And you can automate a lot of that's all. A lot of that's automated, right? It's automatically generating stuff for you. Yeah. I've got this other strand of work where we can automatically generate code as well, right? It's just slightly different, right? But what you've got then is the ability. I think what you've got the ability then to do is bring these things together and say, okay, if we're going to evolve, we've got the framework here, a very clear mathematical framework, very clear semantics that is relatively trivial to mutate and change and do all sorts of cunning stuff too, yeah, which we've never done, right? And so I think it is possible to actually wrap an evolutionary loop around some of this work in order to be able to then have evolutionary approaches generate systems that are relatively trivial, I'll be honest at this point, relatively trivial, but actually would carry some guarantees with them. Yeah, I actually think that's possible to do with this framework. Yeah, although I've never done it. Yeah. Sorry, I kind of went off on one.